Look up at the sky on a clear day, and you'll see the sun shining bright and constant, a familiar ball of light and heat that feels almost predictable. But what if I told you that this seemingly steady star hides secrets far stranger than anything we could imagine? Deep within its turbulent, fiery atmosphere, something mysterious has been observed, something that defies explanation and stirs the imagination. Solar observatories have recently captured eerie, almost ghostly shapes drifting across the sun's surface, formations so unusual they've been nicknamed solar ghosts. These aren't just bursts of energy or typical solar flares. They look like apparitions, shimmering and shifting in ways that challenge everything we thought we knew about our nearest star. Picture immense structures, faint and luminous, dancing at the edges of sunspots and coronal loops. They appear without warning, linger like cosmic phantoms, and vanish just as mysteriously, leaving scientists both fascinated and deeply puzzled. What are these solar ghosts? Could they be a previously unknown form of solar activity, or something even more extraordinary? The sheer scale is staggering. Some of these formations are larger than our entire planet, moving with an otherworldly grace against the sun's violent backdrop. It's a reminder that, even after centuries of observation, the universe still holds marvels that push the boundaries of science and spark our sense of wonder. This video is an invitation to join a journey into one of space's most captivating mysteries. We'll explore the cutting-edge technology that allows us to see these solar ghosts in stunning detail, hear from the researchers trying to decode their origins, and dive into theories that range from magnetic anomalies to phenomena we haven't even named yet. You're about to witness a side of the sun few have ever seen, a realm where science meets the surreal, and where each new discovery feels like stepping into the unknown. So settle in, open your mind to the possibilities, and let's uncover the secrets behind these haunting solar apparitions together. So what exactly are these solar ghosts we're talking about? Think of them as the sun's most elusive and haunting performers, appearing only under the most specific conditions. Scientifically, they're known as transient coronal filaments, faint, wispy structures made of incredibly hot, magnetically confined plasma that drift through the sun's outer atmosphere, the corona. Unlike the bright, explosive drama of solar flares or the distinct darkness of sunspots, solar ghosts are subtle. They're like delicate veils of ionized gas, shimmering with a pale luminosity that makes them look almost ethereal against the sun's fierce brightness. Their filament-like forms can stretch for tens of thousands of kilometers, often weaving through the complex architecture of magnetic loops near active regions on the solar surface. One of the most fascinating things about these structures is how they reveal themselves. Under normal circumstances, the overwhelming glare of the sun makes them nearly impossible to see. It's only during brief, precious moments like a total solar eclipse, when the moon perfectly blocks the sun's main disk, that these faint features become visible to the human eye as pearly, hair-thin strands extending into the darkened sky. But beyond these rare celestial events, it's advanced technology that truly brings them to light. Instruments like NASA's Solar Dynamics Observatory, equipped with high-resolution cameras and filters that isolate specific wavelengths of extreme ultraviolet light, allow us to detect the subtle emissions from these structures. They show up as intricate dancing forms that seem to materialize out of nowhere, linger like cosmic apparitions, and then fade back into the sun's turbulent atmosphere. The reason they appear so ghostly lies in their physical nature. These filaments are sculpted by the sun's powerful magnetic fields, which trap and guide superheated plasma into slender, elongated shapes. Because they're less dense and slightly cooler than the surrounding corona, though still searing at over 1 million degrees Celsius, they stand out as dark, sinuous lines when viewed against the solar disk, but as bright, glowing threads when seen against the blackness of space during an eclipse. This duality adds to their mysterious allure. They are not static features, they evolve, shift, and sometimes even erupt, releasing energy and material back into the solar wind. Their transient behavior means that catching them is like capturing a glimpse of something otherworldly, a fleeting signature of the sun's hidden, dynamic life that challenges both our instruments and our understanding. While these solar apparitions feel like a modern discovery, the truth is that humanity has been catching fleeting glimpses of them for centuries, long before we had the language or the lenses to understand what we were seeing. Early astronomers, equipped with nothing more than rudimentary telescopes and smoked glass to protect their eyes, would occasionally note strange, inexplicable features during their solar observations. They described what they saw as delicate veils, subtle hazes, or gossamer threads that would momentarily shroud the sun's edge or appear near sunspots before vanishing without a trace. Without the technology to capture these transient events, most of these accounts were relegated to the margins of scientific journals, often dismissed as mere optical illusions, atmospheric distortions, or frustrating artifacts within their imperfect instruments. The sheer brevity of these appearances made systematic study nearly impossible, leaving these early witnesses without the evidence to prove they had seen something real. One of the most compelling historical records comes from observations made during total solar eclipses, nature's perfect cosmic laboratory. For a few precious seconds, when the moon completely obscures the sun's brilliant face, the ethereal corona is revealed in all its glory. 19th century eclipse expeditions, often mounted with great difficulty to remote corners of the globe, produced detailed drawings from astronomers who were utterly captivated by the sight. Their sketches frequently included descriptions of luminous filaments and pearly streamers that extended far into the solar atmosphere, features we now recognize as the very phenomena we call solar ghosts. At the time, these scientists lacked the spectroscopic tools to analyze the light from these structures, so they could only document their shape and position, wondering about their true nature and composition. The real turning point came with the dawn of astrophysics and the invention of the spectroheliograph in the late 19th century. This revolutionary instrument allowed astronomers to photograph the sun in specific wavelengths of light, effectively peeling back layers of the solar atmosphere to isolate different elements and temperatures. For the first time, those faint, veiled structures weren't just fleeting visual mysteries. They left a permanent, measurable imprint on a photographic plate. This was the first hard evidence that these hazes were not illusions but tangible physical phenomena, composed of hot, ionized gas and intimately tied to the sun's magnetic activity. It validated the centuries of anecdotal reports and set the stage for the dedicated, technology-driven hunt that would follow, ultimately leading to their identification as the transient coronal filaments we're studying today. This unique window of visibility is precisely why solar eclipses have been so instrumental in the hunt for these elusive phenomena. When the moon slides perfectly in front of the sun, it performs a remarkable feat of natural engineering. It acts like the ultimate lens cap, blocking the overwhelming glare from the sun's main body, known as the photosphere. Suddenly, the million-degree outer atmosphere, the corona, shimmers into view, a delicate halo of pearly white light against the blackened sky. In that profound darkness, the faintest structures become shockingly clear. What was once invisible to the naked eye is now laid bare, vast, intricate loops and ethereal, veil-like filaments stretching millions of kilometers into space. These are the solar ghosts, and for those brief moments of totality, they are no longer hidden. The value of an eclipse goes far beyond this spectacular visual show. It provides a pristine, natural laboratory. Scientists can study the sun's faintest features without the need for artificial coronagraphs, instruments on satellites that use a metal disk to create an artificial eclipse. While those tools are invaluable for daily observation, they can sometimes introduce scattered light or diffraction artifacts that complicate the analysis of the dimmest coronal structures. An actual eclipse, however, offers a perfectly dark, clean backdrop with no man-made obstructions. This allows for incredibly precise measurements of the shape, movement, and brightness of these ghostly filaments, giving researchers a pure, uncontaminated view that is otherwise impossible to achieve. Historically, some of the most compelling early evidence for these apparitions came from eclipse expeditions. Before the space age, these events were like scientific Super Bowls, with astronomers traveling across the globe, hauling tons of delicate equipment, all for a chance at a few minutes or even seconds of critical data. Their photographic plates and hand-drawn sketches from eclipses over a century ago consistently captured details we now recognize as solar ghosts. They documented wispy plumes and faint radial streaks that seemed to defy explanation at the time. Today, we can look back at those historical records and clearly identify the telltale signs of transient coronal filaments, validating those early observations and adding a rich, longitudinal dimension to our study of these mysterious solar features. The modern era has transformed this process. Now, during an eclipse, teams of scientists deploy a battery of sophisticated instruments. High-speed cameras capture video at thousands of frames per second to track the rapid, subtle motions of these plasma structures. Spectrographs break down the faint light from the ghosts into its individual wavelengths, revealing their exact chemical composition and temperature, data that is crucial for understanding what they are made of and how they are energized. This synergy between an ancient celestial event and cutting-edge technology is what pushes our understanding forward. Each total solar eclipse provides a new, golden opportunity to peer directly into the sun's secretive outer layers and document the hauntingly beautiful dance of its most elusive inhabitants. Capturing these solar ghosts requires more than just looking up at the right moment. It demands a technological symphony of instruments, both in space and on the ground, designed to see what our eyes naturally cannot. Each observatory plays a unique role in this cosmic investigation, acting as a specialized eye tuned to a different part of the sun's story. Leading this charge is NASA's Solar Dynamics Observatory, or SDO, a remarkable spacecraft that has been our unwavering sentinel staring at the sun since its launch in 2010. SDO doesn't just take pictures of the sun, it analyzes it in high definition across multiple wavelengths of light simultaneously. Think of it not as a simple camera, but as a sophisticated scientific interpreter. It uses instruments like the Atmospheric Imaging Assembly, which captures breathtaking images of the sun's full disk every 12 seconds in 10 different wavelengths of extreme ultraviolet light. This is the key. Solar ghosts composed of cooler, denser plasma emit light very faintly at specific wavelengths. By tuning its instruments to these precise frequencies, SDO can isolate the ghosts from the sun's overwhelmingly bright background, revealing their intricate, wispy forms as they snake through the chaotic solar atmosphere. This constant, multi-wavelength vigil allows scientists to not only spot these structures but also track their evolution over time, watching as they form, dance, and dissipate. Joining SDO in this hunt is the European Space Agency's Solar Orbiter, a mission that brings us closer to the sun than any spacecraft before it, equipped with a suite of instruments designed for a more intimate examination. While SDO gives us a magnificent full-disk view from Earth's orbit, Solar Orbiter ventures much closer, flying inside the orbit of Mercury to brave the intense heat and radiation. This proximity provides an unparalleled level of detail. Its high-resolution imager can discern features on the solar surface as small as a few hundred kilometers across, akin to spotting a single city on the sun from millions of miles away. More importantly, Solar Orbiter is beginning to provide the first ever detailed views of the sun's polar regions, areas that are largely hidden from our view here on Earth. This is crucial because the sun's magnetic field, which dictates the behavior of solar ghosts, is believed to have its origins in these mysterious poles. By mapping these uncharted territories, Solar Orbiter helps us understand the global magnetic forces that give birth to these localized, ghostly apparitions. But the technological quest doesn't end in space. Here on Earth, powerful ground-based observatories complement these orbital sentinels with their own unique capabilities. Instruments like the coronagraph are the workhorses of ghost hunting. A coronagraph is, in essence, an artificial eclipse creator. It uses a solid disk placed inside a telescope to precisely block the blinding light of the sun's main disk, just like the moon does during a natural eclipse. This reveals the faint corona, allowing astronomers to study solar ghosts any clear day, not just during those rare celestial alignments. Modern coronagraphs, such as those at the Mauna Loa Solar Observatory in Hawaii, are incredibly sophisticated. They employ tunable filters that can isolate the exact wavelength of light emitted by ionized iron or calcium in the corona elements that are prevalent in these ghostly filaments. By combining these observations with adaptive optics systems that correct for the blurring effect of Earth's atmosphere in real time, ground-based telescopes can now produce images of the sun's outer atmosphere that rival the clarity of those taken from space, providing a continuous and complementary stream of data that helps piece together the full life cycle of these enigmatic structures. To truly appreciate the haunting beauty of these solar ghosts, we need to examine their incredible physical characteristics, which are as extreme as they are elegant. At their core, these apparitions are sculpted from superheated plasma, a fourth state of matter where gas becomes so intensely hot that its atoms are torn apart, leaving behind a swirling soup of charged particles like electrons and ions. This isn't just hot, we're talking about temperatures that consistently range between 50,000 and 1 million degrees Celsius. It's a searing, electrified fabric woven by the sun's invisible magnetic forces, and it's this fundamental composition that allows them to glow with that faint, otherworldly luminescence against the darker backdrop of space. The sheer scale of these structures is almost impossible to fully grasp. While they may appear as delicate, wispy threads in images, many of these filaments can stretch for hundreds of thousands of kilometers across the solar surface. To put that into perspective, a single solar ghost can easily dwarf our entire planet. You could line up dozens of Earths end to end and still not match the length of some of the larger formations. They aren't just long, they possess a remarkable and almost paradoxical delicacy. Their most defining visual trait is their near transparency. Unlike the dense, bright chaos of a solar flare, these ghosts appear ethereal and faint, like celestial cobwebs caught in a cosmic breeze. This transparency is a direct result of their lower density compared to the surrounding coronal plasma, allowing the brighter light from behind and beneath them to shine through, which only enhances their phantom-like appearance. Perhaps their most mesmerizing quality is their motion. In a realm dominated by violent, explosive outbursts that can unleash energy equivalent to billions of atomic bombs, solar ghosts move with a surprising and graceful slowness. They don't erupt, they drift, they don't explode, they glide. Observing time-lapse footage from solar observatories reveals these vast structures slowly undulating and shifting, their movements measured and fluid, as if they're dancing to a silent, slow-motion ballet. This graceful choreography is dictated entirely by the subtle shifts and realignments of the sun's powerful magnetic field lines, which act as invisible rails guiding the plasma. This stark contrast to the sun's more aggressive phenomena is what makes them so captivating. They are a demonstration of serene, controlled power amidst a constant storm of solar fury, a hauntingly beautiful reminder of the complex and varied forces at play on our dynamic star. Now, as we zoom in on these solar ghosts with our high-tech observatories, we begin to see they are not all the same. They appear in several distinct forms, each with its own architecture and behavior, suggesting that different forces are at work in their creation. The first and perhaps most common type are the loop-like ghosts. These formations look like immense, faint arches or bridges of glowing plasma, often connecting two points of opposite magnetic polarity on the Sun's surface. They trace the path of the magnetic field lines that have risen up from the solar interior, acting like luminous highways for charged particles. These loops can remain stable for days, slowly shifting and swaying as the magnetic landscape beneath them changes, offering a relatively stable, though still transient, glimpse into the Sun's complex magnetic skeleton. A second, more dramatic category is the radial streamer. These are the classic pearly white extensions that stretch far out into the corona, often visible during a total solar eclipse. Unlike the confined loops, radial streamers project outward from the Sun's surface like giant, luminous spokes on a wheel. They are typically found over areas where the Sun's magnetic field is open, allowing solar wind to flow more freely out into the solar system. Within these broad streamers, finer, hair-like ghostly filaments can often be seen, aligned with the magnetic field and flowing away from the Sun. Their immense length and relatively stable structure make them a key feature for scientists studying how the solar wind is accelerated and energized before it begins its journey across the cosmos. Then there are the fan-shaped formations, which are among the most complex and puzzling structures. These appear as broad, diffuse veils of plasma that seem to spray out from a single point, creating a delicate, curtain-like effect. They are often associated with the boundaries of large coronal holes, regions where the Sun's magnetic field opens up into space. The physics behind these fans is particularly intriguing. They may represent the gradual expansion of magnetic field lines as they stretch away from the Sun, with plasma spreading out to fill the widening volume. Watching a time-lapse of a fan-shaped ghost is like observing a slow-motion geyser of magnetized gas, a beautiful and persistent flow that highlights the gentle yet powerful forces constantly reshaping the corona. Each of these types tells a different part of the Sun's story. The loop-like ghosts reveal the closed magnetic structures that trap and contain plasma, often storing energy that could one day be released in a flare. The radial streamers map the open magnetic highways that guide the perpetual outflow of the solar wind, directly connecting the Sun's surface to the planets. And the fan-shaped formations illustrate the transitional zones where closed fields begin to open up, a crucial interface in understanding how the corona heats and expands. By categorizing their shapes and tracing their evolution, researchers can start to decode the specific magnetic and plasma conditions that give rise to each phantom form, moving us closer to understanding why these beautiful, haunting structures come to be. To truly understand the nature of these solar ghosts, we must look past their ethereal glow and recognize them for what they truly are, the ultimate tracers of the invisible. The Sun is not just a ball of fire, it is a colossal, dynamic magnet, and its power extends far beyond its visible surface through an immense and complex magnetic field. This field is the master architect of everything we see in the corona, from violent flares to the most delicate filaments. Solar ghosts are perhaps its most elegant and revealing signature. They are not free floating clouds of gas, they are structures entirely defined and sculpted by magnetic forces. The superheated plasma that forms them is essentially trapped, forced to flow along the pathways carved by these invisible lines of force like cars confined to a highway. Without the magnetic field, these beautiful, intricate shapes would simply not exist. They are a visual map, a luminous sketch drawn by magnetism itself onto the canvas of the solar atmosphere. This relationship means that by simply observing the form and motion of a solar ghost, scientists can indirectly chart the structure of the magnetic field in the Sun's outer layers, a region where taking direct measurements is currently impossible. The graceful, arching loop of a ghost tells us that the magnetic field beneath it is also arched, likely connecting two areas of opposite magnetic polarity on the solar surface. A long, radial streamer points to a magnetic field line that is open, stretching out into interplanetary space rather than looping back down. When these structures gently sway or oscillate, it's not a random drift. It's a direct response to waves traveling along the magnetic field lines, much like plucking a guitar string. By studying these oscillations, researchers can perform a technique called magnetoseismology, using the plasma's motion to deduce the density, tension, and strength of the magnetic field that guides it. In this way, every faint, shimmering ghost becomes an invaluable tool for probing the sun's hidden magnetic skeleton. The process of their formation is a fascinating dance between plasma and magnetism. It often begins with a slight instability in the sun's magnetic field, perhaps caused by turbulent motions of plasma churning beneath the surface. As magnetic field lines rise and rearrange, they create channels and loops in the corona. Dense, cooler plasma from the lower solar atmosphere is then siphoned up along these lines, filling the magnetic structures and making them visible to our instruments. This is why these apparitions appear so perfectly defined. They are literally outlining the architecture of the magnetic field. Their transient nature is also a magnetic story. They persist only as long as the magnetic configuration that supports them remains stable. A sudden shift or reconnection of those field lines, a process where magnetic lines break and rapidly reform in a new geometry, can cause the ghost to destabilize. It might gently dissipate, its plasma scattering back into the corona, or in more dramatic cases, it can be ejected outward in a slow, majestic release called a coronal mass ejection, sending a part of the sun's ghostly atmosphere streaming across the solar system. While solar ghosts share the stage with some of the sun's most dramatic performers, they belong to an entirely different class of phenomenon, distinguished by their subtlety and persistence rather than their power. To appreciate their unique nature, it helps to contrast them with the solar activity we're more familiar with. Take a solar prominence, for instance. At first glance, a large, looping prominence might look similar to a ghostly filament, and in a way they are relatives. Both are composed of cooler, denser plasma levitating within the sun's corona, held aloft by magnetic fields. The critical difference, however, lies in their visibility and behavior. A prominence is a brilliant, obvious structure, often seen as a bright loop projecting from the sun's limb. It's a dense concentration of plasma that shines brightly because we view it against the dark backdrop of space. A solar ghost, on the other hand, is that same basic structure seen from a different angle. When a prominence is viewed from above, silhouetted against the sun's intensely bright surface, it appears as a dark, snaking line called a filament. But a true solar ghost is even more elusive. It is often a remnant or a much fainter, more diffuse version of these structures, lacking the density to appear as a stark dark line, and instead manifesting as a pale, semi-transparent wisp that is incredibly difficult to detect without specialized tools. The contrast becomes even starker when we compare ghosts to solar flares and coronal mass ejections. These events are the sun's tantrums, sudden, catastrophic releases of immense magnetic energy. A solar flare is a tremendous explosion of radiation across the electromagnetic spectrum, from radio waves to X-rays, unleashing in mere minutes the energy of millions of hydrogen bombs. It is a blinding, rapid-fire event that can disrupt communications and create beautiful auroras on Earth. A coronal mass ejection, or CME, is its material counterpart, a massive bubble of magnetized plasma violently blasted away from the sun at millions of miles per hour. Both are defined by their explosive violence and their profound impact on space weather. A solar ghost is the absolute antithesis of this drama. It does not explode. It does not erupt with fury. It represents a state of magnetic equilibrium and gentle flow. Its energy is not released in a sudden cataclysm, but is instead slowly radiated away or dissipated over time. Where a flare is a shout, a ghost is a whisper. This fundamental difference in energy release is what makes them so fascinating to scientists. Flares and CMEs are all about the rapid conversion of stored magnetic energy into light, heat, and motion. They are the breakdown of an unstable system. Solar ghosts, however, often represent a stable, or at least a long-lived magnetic configuration. They are not storing energy for a dramatic outburst. They are simply tracing the quiet, ongoing pathways of the solar magnetic field. Their persistence is another key differentiator. A major flare might last for an hour. A CME travels through space in a matter of days, but a solar ghost can maintain its delicate structure for many days, sometimes even weeks, slowly evolving and dancing in the corona. This longevity provides a valuable window into the more gradual, sustained processes that shape the solar atmosphere, processes that are just as important as the explosions for understanding our star's long-term behavior. They remind us that the sun's story isn't written solely in its outbursts, but also in the patient, hauntingly beautiful movements of its most delicate features. So if these solar ghosts aren't simply faint prominences and they don't explode with the violence of a flare, how do they actually come into being? The leading scientific theory points to one of the most fundamental and powerful processes shaping our star's atmosphere, a phenomenon known as magnetic reconnection. Picture the sun's magnetic field not as a static, rigid structure, but as a living, dynamic web of invisible lines of force. These lines are constantly moving, twisting, and getting tangled by the churning motions of plasma beneath the solar surface. Now imagine two powerful magnets being slowly pushed together. There's a point where the pressure becomes too great. The opposing fields can no longer maintain their separate structures, and they suddenly snap, breaking, and then rapidly reforming into a new, more stable configuration. This explosive breaking and realigning is the essence of magnetic reconnection, and it's this process that many researchers believe is the primary architect behind these ghostly forms. During a reconnection event, a colossal amount of magnetic energy is converted almost instantaneously into heat and kinetic energy. It's this sudden, localized heating that can supercharge the plasma in that specific region without the cataclysmic blast of a flare. Think of it not as a bomb going off, but as a precise, powerful welder's torch applying intense heat to a very specific area, enough to energize the plasma and cause it to glow brightly in certain wavelengths, yet contained enough to create a structured, sustained form rather than a chaotic explosion. The newly reformed magnetic field lines after reconnection often create a new topology, a new pathway or a new loop. And it is along these freshly minted magnetic rails that the energized plasma is channeled, flowing into the distinctive, faintly luminous shapes we identify as solar ghosts. This theory elegantly explains several of their most puzzling characteristics. Their transient nature makes perfect sense because the magnetic configurations born from reconnection are often temporary themselves, lasting only until the next shift in the magnetic landscape. Their structured appearance is a direct map of the new magnetic geometry created by the reconnection process, and perhaps most importantly, this model accounts for their incredible heat. The sun's corona is mysteriously millions of degrees hotter than the surface below, a paradox that has baffled scientists for decades. Magnetic reconnection is one of the prime suspects for solving this mystery, as it is a fantastically efficient engine for converting magnetic energy into thermal energy. In this view, every solar ghost we observe could be a visible signature of this coronal heating process in action, a gentle, structured release of energy that helps maintain the corona's searing temperatures, making these apparitions not just beautiful anomalies, but key players in the ongoing story of our star's dynamic atmosphere. While magnetic reconnection provides a compelling explanation, it's far from the only idea on the table. Some scientists propose a more rhythmic and continuous process for creating these solar phantoms, one driven not by sudden magnetic snaps but by the constant, undulating pulse of waves. This alternative theory centers on magneto-hydrodynamic waves, a complex but beautiful concept that essentially treats the sun's magnetized plasma as a vast cosmic instrument capable of carrying energy through vibrations. The most famous of these are Alfvén waves, named after the Nobel Prize-winning scientist Hans Alfvén, who first predicted their existence. Imagine plucking a single, incredibly taut guitar string that stretches across the entire solar system. The vibration that travels along that string is a good analogy for an Alfvén wave. It's a wave of magnetic tension and plasma motion that propagates along the sun's magnetic field lines, carrying energy from the turbulent solar surface up into the waiting corona. This wave heating theory suggests that these relentless vibrations could be the gentle artists behind the solar ghosts. As these powerful waves travel upwards, they don't just move, they transfer their energy to the plasma they pass through, effectively giving it a steady, rhythmic push that heats it up. It's a less violent process than reconnection, more like the steady friction of rubbing your hands together to generate warmth rather than the sudden spark of a match. In regions where these waves are particularly strong or focused, this sustained energy input could be sufficient to illuminate the plasma just enough to make it visible as one of those faint, shimmering structures. The graceful, undulating motion we sometimes observe in solar ghosts could literally be the visible signature of these waves passing through, making the plasma itself dance to the magnetic music of the sun. The appeal of this theory lies in its ability to explain the more serene and persistent nature of many ghosts. Magnetic reconnection is inherently an event. It happens and then it's over. But the sun's interior is a constant roiling furnace of convection, which should generate a non-stop symphony of these magnetohydrodynamic waves, providing a continuous energy supply to the corona. This could account for why some ghostly structures appear to form and persist for such long periods without any obvious explosive trigger. They are being constantly fed and sustained by this wave energy, a perpetual flow that maintains their delicate balance against the dissipating effects of the corona. They would be less like a sudden apparition and more like a standing wave in a river, a feature that appears stable but is in fact maintained by a constant, powerful current flowing beneath the surface. Deciding between these theories or determining if both are at play is an active and challenging area of research. The difficulty lies in detection. The motions and energy transfers involved in wave heating are incredibly subtle, often operating at scales and speeds that push the very limits of our current observatories. Proving this theory requires not just seeing a structure, but meticulously measuring tiny, periodic oscillations within it, tracking the precise flow of energy from a wave into the surrounding plasma. New data from missions like the Parker Solar Probe, which flies through the corona itself, and the continued ultra-high-resolution observations from Solar Orbiter are providing tantalizing clues. They are detecting signatures of these waves and tracing how their energy dissipates, offering growing support for the idea that the sun's magnetic music is indeed a powerful force in shaping the haunting beauty of its most ethereal inhabitants. This brings us to one of the most profound implications of these ghostly structures, their potential role as a hidden source of the solar wind. For decades, scientists have worked to solve a fundamental solar mystery. We know a perpetual stream of charged particles, the solar wind, flows outward from the sun at immense speeds, bathing the entire solar system and defining the very boundaries of interstellar space. But pinning down exactly where and how this wind is born within the sun's chaotic atmosphere has been an immense challenge. The discovery and detailed observation of solar ghosts is providing a compelling new piece to this cosmic puzzle. Many researchers now theorize that these faint, wispy formations are not just passive tracers of magnetic fields. They may be active, dynamic regions where the solar wind itself is catalyzed and accelerated on its journey into the void. The connection lies in the specific type of magnetic structures these ghosts often inhabit. Many appear in and around the boundaries of what are known as coronal holes. These are vast, dark regions in the sun's corona where the magnetic field lines are open, stretching out into space rather than looping back to the solar surface. It's like a door has been left open, and the superheated plasma from the corona can flow out freely along these magnetic highways. Within these holes, the fine, veil-like structure of a solar ghost suggests an area of incredibly complex and tangled magnetic topology. It's within this messy, energetic interface that the magic might happen. The gentle, sustained heating processes that form the ghosts, whether from magnetic reconnection or wave energy, could provide the final, critical push that energizes particles enough to escape the sun's powerful gravity and become the solar wind. Evidence for this theory is mounting thanks to our fleet of solar observatories. By combining extreme ultraviolet images from SDO that show the delicate structure of a ghost with particle and magnetic field data collected by the Parker Solar Probe as it flies through the solar wind, scientists can start to draw a direct line from cause to effect. They can observe a particular ghostly formation near a coronal hole and then, days later, measure a specific signature in the solar wind particles that reach Parker, a signature that matches the unique composition and velocity predicted to come from that very type of structure. It's a form of cosmic forensics, tracing the solar wind back to its source. This research suggests that these apparitions are not merely scenic features. They are likely fundamental contributors to the slow solar wind, the steadier, denser component of this perpetual outflow. Their slow, graceful evolution provides a constant, gentle feed of material into space, a stark contrast to the violent, sporadic injections from coronal mass ejections. Understanding this link is not just an academic exercise, it's crucial for improving our ability to predict space weather. The solar wind is the primary driver of conditions in the space between planets. Its speed, density, and magnetic orientation determine whether we'll see brilliant auroras dancing at the poles or whether we might face potential disruptions to satellite operations, power grids, and astronaut safety. If solar ghosts are indeed key source regions, then monitoring their formation, size, and location becomes a powerful new tool for forecasters. A large, complex ghost forming along the edge of a coronal hole that is facing Earth could be a predictor that a stream of faster, denser solar wind is on its way, due to arrive at our planet in a matter of days. By learning to read these faint, haunting signatures on the sun, we move closer to forecasting the conditions in our own cosmic neighborhood with greater accuracy and lead time, transforming these ethereal phantoms from mere curiosities into vital signposts for life on our technologically dependent planet. Their lifespan is one of the most defining and fascinating aspects of these solar apparitions, offering a stark contrast to the sun's more fleeting outbursts. Unlike a solar flare, which can unleash its incredible fury in a matter of minutes before fading away, a solar ghost is a study in patience and persistence. These structures don't live fast and die young. They embody a slow, graceful ballet that can unfold over many days. Observatories have documented individual ghosts maintaining their delicate, wispy forms for periods ranging from several hours to well over a week, with some particularly stable formations even lingering for multiple solar rotations. This remarkable longevity provides scientists with a rare and valuable opportunity. It allows them to observe the subtle, continuous processes that shape the corona over time, rather than just capturing a single, explosive snapshot. The life of a solar ghost is not one of static existence. From the moment it first shimmers into view, it is in a constant state of slow, deliberate evolution. Its journey typically begins with a formation phase, where we see the faint outline of the structure gradually brighten and become more defined as plasma flows along newly established magnetic pathways. This isn't a sudden apparition, it's a slow materialization, like a photograph developing in a darkroom. Once fully formed, the ghost enters what scientists call a quasi-stable phase. This is the heart of its lifespan, where it maintains its overall structure while still undergoing constant, subtle change. Its filamentary body might gently sway or oscillate, responding to waves traveling along its magnetic spine. Smaller strands within the larger formation might brighten, fade, or realign, revealing the dynamic flow of energy and matter within the seemingly stable form. This period of slow evolution is like watching a cloud change shape on a breezy day. The overall presence is constant, but its minute details are always in flux. This extended performance eventually winds down during the dissipation phase, but even its end is typically a gentle affair, not a dramatic collapse. The plasma that makes up the ghost might slowly drain back down along the magnetic field lines to the solar surface, like water receding from a beach. Alternatively, the supporting magnetic structure itself might gradually weaken or reconfigure, causing the ghost to simply fade from view as the plasma disperses evenly into the surrounding corona. In rarer, more dramatic cases, this stable configuration can become unstable, leading to a gradual lift-off where the entire structure peacefully detaches and is carried away by the solar wind. This entire life cycle, from birth to death, provides a continuous narrative of the sun's magnetic activity, a story that is completely missed if we only focus on its most violent and brief explosions. This temporal behavior makes solar ghosts invaluable to researchers. Their persistence acts as a natural tracer, allowing scientists to map the slow, large-scale movements of the sun's magnetic field over time. By tracking the same ghost for days, they can measure how the magnetic landscape is shifting and evolving, providing clues about the dynamics happening deep beneath the visible surface. Furthermore, their long lifespan means that multiple observatories, both in space and on the ground, can coordinate to observe the same structure from different angles and with different instruments over an extended period. This creates a rich, multi-dimensional dataset that is simply impossible to gather for a transient event like a flare. In essence, these enduring phantoms give us a front-row seat to the sun's long-term atmospheric dynamics, revealing the quiet, sustained processes that play an equally important role in shaping our star's character as its more famous and furious outbursts. So how do we move beyond simply seeing these ethereal shapes and begin to understand what they are physically made of? The answer lies in a powerful technique called spectroscopy, which allows us to dissect the very light these structures emit and read it like a cosmic barcode, revealing their elemental secrets. When a solar ghost shimmers in the corona, it isn't just emitting a uniform white light. It's broadcasting a complex spectrum of colors, each one a unique signature of a specific chemical element in a particular state. By using instruments called spectrographs attached to solar telescopes, both on spacecraft and here on Earth, scientists can capture this light and spread it out into its constituent wavelengths, creating a detailed graph that shows bright emission lines at very specific points. Each of those lines is a direct fingerprint shouting the presence of a specific element like hydrogen, helium, or iron that has been stripped of some or all of its electrons, a state we call ionized. This spectral analysis has provided a definitive answer to the question of composition. Solar ghosts are primarily sculpted from a searing hot, ionized gas known as plasma. The overwhelming majority of this plasma is made up of ionized hydrogen, the most fundamental building block of the universe, which has had its single electron stripped away. This is followed by a significant amount of ionized helium, the second most abundant element in the sun. But the real story, the one that helps unlock deeper mysteries, is told by the trace elements, the heavier atoms like carbon, nitrogen, oxygen, and most importantly, iron. These elements, while present in much smaller quantities, are incredibly efficient at emitting light in the extreme ultraviolet wavelengths that our space-based observatories are designed to detect. In particular, highly ionized iron atoms iron that has lost 14 or even 15 of its electrons create some of the most prominent and useful emission lines for studying these faint structures. The mere fact that we can detect this highly ionized iron is a crucial clue, as it requires a consistent source of intense heat to keep iron in such a thoroughly stripped-down state. This is where the study of solar ghosts makes one of its most significant contributions, helping to solve the enduring mystery of coronal heating, For over half a century, scientists have been baffled by the fact that the Sun's outer atmosphere, the corona, is millions of degrees Celsius hotter than the solar surface directly below it. It's as if the air around a light bulb were somehow hotter than the bulb's glass surface itself. It completely defies intuition. The composition of these ghosts, as revealed by spectroscopy, provides critical evidence for the two leading theories we discussed. If the primary heating mechanism were violent, large-scale magnetic reconnection events, we would expect to see spectroscopic signatures of very rapid and extreme heating. Certain spectral lines would brighten intensely and then fade quickly. Alternatively, if the gentle, continuous energy input from magneto-hydrodynamic waves is the dominant process, the spectral lines would show subtler, more rhythmic fluctuations in their intensity and width. By meticulously observing how the light from these iron and other ionized traces changes over the lifespan of a ghost, researchers can essentially take the temperature of the plasma in real time and measure how that energy is being delivered, providing a crucial test to distinguish between these competing ideas and finally explain why the Sun's atmosphere is so unbelievably hot. Perhaps no single event has done more to bring solar ghosts into the public and scientific spotlight than the Great American Eclipse of August 21, 2017. As the moon's shadow raced across the United States from Oregon to South Carolina, it provided a pristine, nationwide viewing platform for one of nature's most awe-inspiring spectacles. But for astronomers, this wasn't just a public event. It was a once-in-a-generation scientific opportunity. Dozens of research teams, from professional observatories to university-led citizen science projects, positioned themselves along the path of totality with one unified goal: to capture the Sun's corona in unprecedented detail. What they recorded would become a treasure trove of data, fundamentally shifting our perspective on how common and complex these elusive ghost structures truly are. The conditions that day were uniquely perfect for ghost hunting. The Sun was nearing the minimum of its 11-year activity cycle, a period when the corona typically exhibits more structured, streamer-rich features rather than the chaotic, flare-filled landscape of solar maximum. This quieter state provided a clearer, less cluttered view of the delicate coronal fine structure. As the moon slid into place and daylight vanished, cameras across the continent began capturing images that left researchers breathless. The corona revealed itself not as a simple, fuzzy halo of light, but as a breathtakingly intricate tapestry of luminous filaments, radiant streamers, and vast feathery plumes stretching millions of kilometers into the blackness of space. These weren't the vague, theoretical structures from textbooks. They were stunningly sharp and defined, and they were everywhere. One of the most comprehensive datasets came from a project led by the National Center for Atmospheric Research, which deployed a network of identical, specially designed cameras at multiple sites along the eclipse path. This strategic setup allowed them to capture continuous, high-resolution observations of the corona for the full 90 minutes it took the moon's shadow to cross the country. By stitching this data together, they created a time-lapse movie of the corona with a clarity and duration never before achieved from the ground. This moving portrait was a revelation. It showed the solar ghosts not as static pictures, but as dynamic, evolving entities. Researchers could clearly see faint plasma structures gently oscillating, like waves moving through a field of grass. They witnessed the slow expansion of radial streamers and could track subtle changes in their brightness and shape over the short duration of the eclipse. This proved these features were not frozen sculptures but living, breathing parts of the solar atmosphere, actively responding to magnetic forces in real time. The real breakthrough, however, came from combining these ground-based eclipse images with simultaneous observations from space. While Earth-bound telescopes enjoyed their few minutes of perfect viewing, NASA's Solar Dynamics Observatory and the Solar and Heliospheric Observatory were watching from their vantage points in space, collecting data in the extreme ultraviolet and with their own coronagraphs. By overlaying the incredibly detailed white light eclipse photos onto the magnetic maps and ultraviolet imagery from the spacecraft, scientists could perform a feat of scientific triangulation. For the first time, they could directly and unambiguously link the appearance of a specific, faint, ghostly streamer seen during the eclipse to the precise magnetic conditions on the solar surface below it. They saw how the feet of these vast structures were rooted in regions of mixed magnetic polarity, and how their graceful arcs perfectly traced out the geometry of the magnetic field in the corona, confirming long-held theories about their origins. The legacy of the 2017 eclipse data is still unfolding years later. It provided a statistical bonanza, revealing that these ghostly filaments are far more numerous and complex than previously estimated from satellite data alone. The clean, artifact-free view from the eclipse allowed researchers to develop new computer algorithms to automatically detect and classify these subtle features, techniques that are now being applied to daily satellite observations to find more ghosts than ever before. This single event transformed our understanding from seeing these apparitions as rare curiosities to recognizing them as fundamental, ever-present components of the sun's atmosphere. It was a powerful reminder that sometimes, to see the most elusive secrets of the universe, we simply need to wait for the perfect moment when nature provides the right conditions for the veil to be lifted. To truly see a solar ghost for what it is, you have to learn to look at it through different eyes, or more accurately, through different filters. The light our human eyes perceive is just a tiny sliver of the electromagnetic spectrum, and when we limit ourselves to that visible slice, we miss almost the entire story. The sun is a symphony of light, emitting energy across a vast range of wavelengths, from radio waves to gamma rays. Each of these wavelengths acts like a special filter, isolating specific physical processes and conditions within the solar atmosphere. By tuning our advanced observatories to these different frequencies, we don't just get a single picture of a solar ghost. We get a multi-layered portrait, with each view revealing a unique and crucial piece of the puzzle. Let's start with the view in visible light, the one most familiar to us. During a total solar eclipse, this is what we see with our own eyes: the magnificent pearly white corona with its delicate, hair-like streamers stretching out into the darkness. In this natural light, a solar ghost appears as a faint, wispy structure of integrated brightness, a beautiful but ultimately simplistic silhouette. We can see its shape and its general location, but we learn very little about its temperature, its density, or the dynamic forces acting upon it. It's like looking at the shadow of a person. You can discern their outline, but you cannot see the color of their eyes, the expression on their face, or the clothes they are wearing. The visible light view gives us the ghost's basic form, but it hides its true physical nature. This is where the extreme ultraviolet, or UV, part of the spectrum becomes absolutely essential. Spacecraft like the Solar Dynamics Observatory are equipped with instruments specifically designed to see the sun in these shorter, more energetic wavelengths, which are completely blocked by Earth's atmosphere. The corona, with its searing million-degree temperatures, is an incredibly bright emitter of UV light. But not all UV light is the same. Different wavelengths correspond to light emitted by specific chemical elements that have been ionized to different degrees. For instance, one filter might isolate light emitted by iron that has lost 11 electrons, which occurs at around 1 million degrees Celsius. Another filter might capture light from helium that has lost 1 electron, which happens at a slightly cooler 20,000 degrees. When we point these specialized UV filters at a solar ghost, the structure transforms before our eyes. In a wavelength that highlights 1 million degree plasma, the ghost might appear as a bright, intricate network of fine loops, vividly tracing the pathways of intense magnetic fields. Switch to a filter tuned to a slightly cooler temperature, and that same structure might almost vanish, only to be replaced by a different, fainter set of features in another location. This multi-wavelength analysis is the key to unlocking the ghost's thermal structure. It allows scientists to create a detailed temperature map, showing which parts of the ghost are the hottest and which are relatively cooler, revealing where energy is being most efficiently deposited and dissipated. But the diagnostic power doesn't stop at temperature. The precise intensity of the light in each wavelength also provides a direct measure of the plasma's density, how many particles are packed into a given volume. A brighter emission in a specific EUV band indicates a denser concentration of that particular ion. By comparing the brightness across multiple filters, researchers can calculate the density throughout the ghost structure. This reveals that these are not uniform clouds of gas. They have a complex internal anatomy with a dense, cooler core of plasma likely channeled along the central axis of the magnetic field, surrounded by a hotter, more tenuous sheath. This density gradient is critical for understanding how the structure maintains its stability against the intense pressure of the surrounding corona. Perhaps the most profound revelation from this multi-wavelength approach is how it illuminates the ghost's relationship with the magnetic field. While we cannot see the magnetic field lines directly, the superheated plasma that comprises the ghost is an obedient tracer forced to flow along these invisible rails. By observing the structure's shape and evolution across multiple temperature bands, scientists can infer the complex three-dimensional architecture of the magnetic field that confines it. They can see how different loops connect where they are rooted on the solar surface and how energy might be transferred between them. An event that might look like a simple, gentle brightening in one wavelength could be revealed in another as a sign of a subtle magnetic reconnection event, a small-scale energy release that helps to heat and sustain the entire structure. Viewing a solar ghost through this multi-spectral lens is the difference between hearing a single instrument play a note and listening to the entire orchestra perform a complex symphony. Each wavelength adds a new instrument to the mix, combining to create a rich, full understanding of one of the sun's most captivating performances. The name Solar Ghosts isn't just a fanciful label dreamed up by a poet. It's a remarkably accurate descriptor that captures the very essence of these perplexing structures. The term ghost perfectly encapsulates their three most defining characteristics: their elusive transparency, their unpredictable and fleeting nature, and their profound air of mystery. Much like a spectral apparition, a solar ghost possesses an almost ethereal quality, a faint and wispy presence that seems to barely exist at all. They don't blaze with the intense, solid light of a prominence or the explosive fury of a flare. Instead, they shimmer with a pale, luminous glow, appearing as semi-transparent veils draped across the sun's brilliant disk. This delicate, barely there appearance is what makes them so challenging to observe, requiring the most advanced technology or the perfect alignment of a total eclipse to bring them into view, as if they are reluctant to be seen by the naked eye. Their behavior further cements the supernatural analogy. They are the phantoms of the solar atmosphere, appearing without any obvious warning, lingering for a time as they perform their slow, graceful dance, and then vanishing just as mysteriously as they arrived. There is no dramatic explosion to mark their end. They simply fade back into the seething background of the corona, leaving no trace behind. This transient, here one, moment gone the next nature is classic ghostly behavior, making them feel like temporary visitors from another realm rather than permanent fixtures of our star. They haunt the edges of active regions and the boundaries of coronal holes, appearing as fleeting signatures of the sun's hidden magnetic life. They're to be studied only if you're looking at precisely the right place at the right time with the right tools. Beyond the visual metaphor, the name also powerfully evokes the sense of profound mystery and scientific intrigue that surrounds them. For centuries, what we now call solar ghosts were little more than unexplained glimpses and unverified reports. The ghost stories told by early astronomers who saw something they couldn't explain. Even today, with our fleet of high-tech observatories, they remain enigmatic. We can see them, measure their temperature, and map their magnetic fields, but we are still actively debating their fundamental origins and the precise mechanics of their formation. They are a lingering puzzle, a haunting question mark in our understanding of solar physics. The name Solar Ghost, therefore, does more than just describe, it inspires. It connects the cold, hard data of science with the innate human fascination with the unexplained, bridging the gap between empirical observation and the timeless wonder of looking up at the sun and realizing it still holds secrets that whisper just beyond our current understanding. Detecting these ethereal structures is one of the most formidable challenges in modern solar physics, a task that pushes our technology to its absolute limits. The primary obstacle is their breathtaking faintness. A solar ghost's luminosity is often millions of times dimmer than the overwhelming glare of the sun's main disk, the photosphere. Trying to see one directly is akin to attempting to spot a single, faint candle flame held right next to a massive, blazing spotlight. This extreme contrast means that even the most advanced telescopes are effectively blinded unless they employ a very specific trick. The solution is the coronagraph, an ingenious instrument that uses a solid occulting disk to artificially block the sun's brilliant face, creating a perpetual artificial eclipse. But even this isn't a perfect fix. No man-made disk can replicate the absolute blackness provided by the moon during a natural eclipse. Inevitably, some light scatters around the edges of the disk, creating a diffuse, bright halo within the instrument that can easily drown out the very faintest details of the coronal structures scientists are desperately trying to study. This forces researchers to develop incredibly complex image processing algorithms to subtract this scattered light, a painstaking process that can sometimes introduce its own artifacts and uncertainties into the data. Compounding this issue of faintness is the sun's own tendency to upstage its subtler performers. The solar atmosphere is a constant theater of violent and dramatic events, solar flares that unleash blinding flashes of X-rays, and coronal mass ejections that erupt with enough force to dwarf entire planets. When one of these events occurs anywhere on the solar disk, it can completely saturate the sensitive detectors on our observatories. The instruments designed to be sensitive enough to capture faint ghosts are suddenly overwhelmed by a flood of intense light and energetic particles. This forces them to automatically lower their sensitivity or temporarily shut down to avoid damage, effectively rendering the entire sun unobservable for the precise, faint features they were meant to study. It's like trying to listen for a whisper at a rock concert. The moment the main act begins, all subtlety is lost. This means that periods of high solar activity, while fascinating in their own right, are ironically the worst times to go hunting for these delicate phantoms, as they are constantly being photobombed by their more explosive stellar siblings. For astronomers using ground-based telescopes, an entirely separate layer of challenge is added: Earth's own atmosphere. Our blanket of air, so essential for life, is the nemesis of clear solar observation. It is turbulent, constantly moving and distorting the light that passes through it, which is why stars appear to twinkle in the night sky. For solar physicists trying to resolve features that may be only a few hundred kilometers across on an object 93 million miles away, this atmospheric turbulence is a devastating problem. It blurs and smears the fine, wispy details of a solar ghost, making it impossible to distinguish its true structure. To combat this, the best ground-based solar observatories like the Daniel K. Inouye Solar Telescope in Hawaii are built on high mountaintops and employ revolutionary adaptive optics systems. These systems use a powerful laser to create an artificial guide star in the upper atmosphere and then measure its twinkle hundreds of times per second. A computer-controlled deformable mirror then flexes and bends in the exact opposite pattern of the atmospheric distortion, canceling it out in real time to provide a crystal-clear view. This technology is a marvel, but it is extraordinarily complex and expensive, and it can only correct for so much. On days of particularly bad atmospheric seeing, even this advanced system can struggle to reveal the sun's most elusive secrets. The haunting dance of solar ghosts may seem like a distant, abstract wonder, but their true importance hits much closer to home, right down to the very technology we rely on every single day. This is because these ethereal structures are not just passive specters, they are active players in the complex system of space weather, and understanding their subtle dynamics could be the key to protecting our modern technological world from the sun's unpredictable temper. Space weather, the constant flow of particles and magnetic fields from the sun, might sound like a scientific curiosity, but its effects are profoundly practical. A powerful burst of charged particles from a coronal mass ejection can slam into Earth's magnetic field, inducing powerful electrical currents in the ground. These geomagnetically induced currents can overload power grids, potentially causing widespread blackouts that last for hours or even days. They can also disrupt the delicate electronics on satellites, crippling global positioning systems, television broadcasts, and crucial military and scientific communications. For astronauts aboard the International Space Station or on future missions to the Moon and Mars, intense solar radiation from these events poses a serious health risk, threatening them with dangerous exposure outside of our planet's protective magnetic shield. This is where the study of solar ghosts moves from fascinating science to critical application. The most damaging space weather events are often preceded by periods of complex magnetic activity on the sun, and this is the very realm where ghosts are born and live out their lives. Many researchers now believe that the formation and behavior of these faint structures serve as an early warning system, a kind of canary in the solar coal mine. Their appearance, particularly around the boundaries of coronal holes, often signals that the sun's magnetic field is in a state of reorganization. This restructuring can create the conditions that lead to larger, more violent events. A stable, long-lived ghost might indicate a period of relative calm, its persistent form reflecting a balanced magnetic configuration. Conversely, the sudden brightening, rapid oscillation, or gradual destabilization of one of these structures could be a visible sign that magnetic stress is building up beneath the surface, energy that might soon be released in a more dramatic and potentially Earth-directed flare or coronal mass ejection. By meticulously documenting the life cycles of these ghosts, how they form, how they evolve, and how they ultimately dissipate, scientists aim to incorporate this new data into sophisticated computer models that simulate the sun's behavior. Current space weather forecasting is good at telling us what is happening now, but it struggles with accurate, long-range prediction. It's like trying to predict a hurricane's path without knowing the precise conditions of the ocean and atmosphere that fuel it. If we can understand the role these ghosts play in the slow buildup of magnetic energy, our models could become vastly more predictive. We might be able to look at the sun and see not just an imminent explosion, but the conditions for one that might occur days from now. A large, complex ghost forming in an Earth-facing coronal hole could become a key data point, signaling forecasters that the probability of a significant solar wind stream or an eruptive event is increasing, giving utility companies, satellite operators, and space agencies precious extra time to enact protective measures. The ultimate goal is to move from reactive monitoring to proactive forecasting. Instead of simply bracing for impact after a major flare has already erupted, we could one day have a space weather forecast that looks much like our terrestrial weather reports, predicting solar storms with lead times of several days. This would allow power grid operators to strategically manage load, temporarily taking vulnerable transformers offline to prevent damage. Satellite companies could safely place their valuable assets into a protective stand by mode, and airline pilots on polar routes could be rerouted to avoid areas of heightened radiation risk. The gentle, whispering signals of solar ghosts, once decoded, could provide the advanced warning we need to shield our technologically dependent civilization from the sun's most powerful outbursts. transforming these ethereal phantoms from objects of pure curiosity into invaluable guardians of our modern way of life. Given their ghostly name and truly otherworldly appearance, it's perhaps no surprise that these solar apparitions have sparked their fair share of imaginative theories and outright myths. One of the most persistent ideas that circulates online is that these structures are somehow evidence of alien technology or extraterrestrial activity, that they might be immense constructs or energy harvesters built by a civilization far more advanced than our own. While this is a thrilling concept for science fiction, the reality, supported by decades of rigorous observation, is simultaneously more ordinary and far more extraordinary. Solar ghosts are not the product of intelligence. They are stunning demonstrations of the fundamental laws of physics playing out on a colossal scale. Every intricate loop, every wispy streamer, is the direct and inevitable result of the interaction between superheated plasma and magnetic fields, a natural process we can replicate in laboratory experiments on Earth and model with incredible precision using supercomputers. The physics that creates them is the same physics that governs the northern lights or the arc of a welding torch, just amplified to a truly astronomical degree. Another common misconception conflates these solar features with signs of impending doom for our planet. Some speculate that their appearance could herald a catastrophic solar event destined to wipe out technology or even life on Earth. It is crucial to understand that while solar ghosts are indeed linked to the sun's magnetic activity, they themselves are typically manifestations of stability, not precursors to imminent destruction. In fact, their long, quiet lifespans often indicate a period of magnetic equilibrium. The truly disruptive solar events' massive flares and coronal mass ejections usually originate from different, more unstable magnetic configurations that are visibly more complex and explosive. Rather than being omens of disaster, the gentle evolution of a solar ghost is more like a sign of the sun's quietly dynamic state, a normal part of its 11-year cycle of activity. Their study actually helps us better predict truly dangerous space weather, making us safer, not warning us of an unavoidable fate. The most important takeaway is that these phenomena are not supernatural or inexplicable. They are solidly, empirically natural. The use of the word ghost is a powerful metaphor for their elusive and transient behavior, not a literal description. There is no mystery of consciousness or intent behind them. Instead, they present a fascinating scientific puzzle of plasma dynamics and magnetic hydrodynamics. The mystery is not whether they are paranormal, but in pinning down the exact mechanisms that heat their plasma and shape their beautiful forms. This distinction is vital because it opens the door to real understanding rather than closing it with supernatural speculation. By accepting that they are natural phenomena, we empower ourselves to study them, to learn from them, and to genuinely appreciate the profound beauty of a universe that can create such breathtaking complexity through the elegant and entirely knowable laws of nature. Recent missions have propelled our understanding of solar ghosts into a new era, providing views so intimate they feel almost invasive. The Parker Solar Probe, a marvel of engineering, has done the unthinkable by flying through the sun's corona itself, venturing closer to our star than any spacecraft in history. It doesn't just take pictures from a distance, it samples the very environment these ghosts call home, measuring the particles, magnetic fields, and plasma waves in situ. This is like moving from studying a hurricane with satellite images to flying a specially equipped plane directly into the storm's eye. The data it has sent back is nothing short of revolutionary, revealing that the boundaries around these ghostly structures are far more dynamic and complex than our remote observations had suggested. Parker has detected intense, localized ripples in the magnetic field and bursts of energetic particles emanating from the regions where ghosts are forming, providing the first direct evidence of the small-scale magnetic reconnection events and plasma waves that are likely responsible for their creation and sustained heat. Meanwhile, the Solar Orbiter mission offers a different but equally vital perspective. Its orbit is designed to give us our first ever clear views of the Sun's polar regions, and the data from these vantage points is already transforming our models. We've long theorized that the Sun's global magnetic field, which dictates the behavior of everything in the corona, has its roots in these mysterious poles. Solar Orbiter has now confirmed that the polar magnetic landscape is a chaotic, rapidly shifting mosaic of small-scale magnetic elements. This chaos appears to be the engine that generates the open magnetic field lines which often cradle the long, radial streamer-type ghosts. The mission's sophisticated suite of instruments can simultaneously image a ghost in extreme ultraviolet light, while precisely measuring the magnetic conditions at its base on the solar surface, creating a direct and unambiguous link between what happens below and what we see above. This has allowed scientists to watch, in near real time, how a shift in the magnetic flux at the pole can trigger the formation of a new, faint filament thousands of kilometers out in the corona within a matter of hours. The synergy between these two missions is where the real magic happens. Parker samples the particle flow from a specific ghostly streamer, and weeks later, when that same solar wind stream passes by Earth, other observatories can analyze it. Solar Orbiter, often positioned at a different angle, can then look back and see exactly what that source region looked like at the time the particles were released. This multi-point observation campaign is like having multiple detectives at a crime scene, each gathering a different type of evidence that, when combined, reveals the whole story. What they are finding is that these ghosts are not merely passive tracers but active contributors, acting as source regions for the slow solar wind. The data suggests that the slow, graceful dissipation of these structures, where plasma gradually bleeds out along magnetic field lines, provides a steady and significant feed of material into the solar wind, constantly shaping the conditions throughout our entire solar system. The quest to unravel the mystery of solar ghosts is far from over. In fact, it's accelerating, with a new generation of missions being designed with these very phantoms in mind. The next wave of solar observatories moves beyond simply observing the sun to interrogating it with unprecedented precision, employing specialized instruments and revolutionary strategies built specifically to detect and analyze its most elusive features. Leading this charge is a mission that promises to be a true game-changer: the National Oceanic and Atmospheric Administration's Space Weather Follow-on Lagrange 1 spacecraft, or SWFO-L1. Scheduled for launch in the coming years, this observatory will occupy a unique vantage point at the Lagrange 1 point, a stable gravitational spot between the Earth and the Sun. Its primary mission is operational space weather forecasting, but it will carry a powerful new coronagraph specifically engineered to study the faint structures of the inner corona with minimal scattered light. This instrument will provide a continuous, high-fidelity stream of data on solar ghosts, allowing scientists to monitor their formation and evolution in near real time, which is crucial for developing the next generation of space weather prediction models. Even more ambitious projects are on the drawing board, aiming to achieve what was once thought impossible: true three-dimensional mapping of the Sun's atmosphere. The European Space Agency is actively studying the concept for a mission called Proba 3, which is a breathtaking feat of precision formation flying. Instead of a single satellite, Proba 3 will consist of two separate spacecraft. One will carry a coronagraph to block the Sun's disk, while the other, flying precisely 150 meters away, will carry the main camera to image the corona. By maintaining this exact formation, they will create an artificial eclipse that can last for hours on end, completely eliminating the problematic scattered light that plagues traditional coronagraphs. This will provide the cleanest, most stable view of the corona ever achieved, revealing the subtle details of solar ghosts with a clarity we can only dream of today. This technology will allow researchers to not just see these structures, but to measure their depth and density in 3 dimensions, finally moving from flat images to a volumetric understanding of their complex architecture. The future doesn't stop with two spacecraft. The ultimate goal is a constellation of solar observatories working in concert. NASA is exploring concepts for a multi-spacecraft mission that would place several identical observatories into different orbits around the Sun. Imagine one spacecraft viewing a solar ghost from the side, another looking directly down on it from above the Sun's pole, and a third measuring the particles flowing from it. This coordinated fleet would provide simultaneous multi-angle observations, allowing scientists to reconstruct a full 3D model of these structures and track how they change over time. This kind of data is essential for finally settling the debate between magnetic reconnection and wave heating, as it would allow researchers to precisely trace the flow of energy through the ghost and pinpoint its origin. It would be like moving from a single stationary security camera to a full array of cameras covering every angle of a room. The difference in understanding would be profound. Back on Earth, ground-based technology is also leaping forward. The next generation of solar telescopes, like the upcoming European Solar Telescope and the planned additions to the Daniel K. Inau Solar Telescope, will be equipped with even more advanced adaptive optics and coronographic systems. These instruments will be capable of resolving features on the Sun's surface down to a scale of just a few tens of kilometers, a resolution that would allow us to see the individual magnetic elements that are thought to be the footpoints of these vast coronal structures. By combining these ultra-high-resolution ground views with the wide-field, multi-wavelength data from space-based missions, solar physicists will be able to connect the micro-scale physics happening at the surface to the macro-scale beauty of the ghosts in the corona, creating a complete and unified picture of solar activity from its smallest origins to its largest consequences. This collaborative, multi-platform approach, harnessing both space-based and terrestrial technology, is our best hope for finally coaxing these solar phantoms to reveal their secrets and, in doing so, unlocking a deeper understanding of our dynamic star. This remarkable ability to decode the Sun's faintest whispers is not just about understanding our own star. It's a master key that unlocks the secrets of stars across the entire cosmos. The detailed physics we're unraveling by studying solar ghosts provides a universal Rosetta Stone for stellar astrophysics, allowing astronomers to interpret the flickering, complex light from stars millions of light-years away. For generations, the coronae of other stars were little more than blurry points of light, their intricate details hopelessly lost in the vastness of space. But with the advent of powerful new telescopes and sophisticated analytical techniques, we are now on the cusp of resolving these distant suns, and the lessons learned from our own sun's phantoms are proving to be absolutely indispensable. The challenge with other stars is one of sheer distance. Even the most powerful telescopes cannot resolve the disk of a typical star's corona. We receive all their light blended into a single tiny point. However, by applying the principles of spectroscopy we use on the Sun, astronomers can still dissect that light. When they observe a star, they are not just seeing a simple white dot. They are capturing a complex spectrum, a unique barcode of emission and absorption lines that reveals the star's chemical composition, temperature, and magnetic activity. Before we understood solar ghosts, certain faint emission lines in stellar spectra, particularly those from highly ionized iron and other trace elements, were puzzling. They indicated the presence of hot, structured plasma, but its origin and behavior were a mystery. Now, armed with the knowledge that these spectral signatures are the telltale fingerprints of ghost-like structures on our Sun, astronomers can confidently attribute them to similar phenomena on other stars. They can look at the subtle variations in these spectral lines and infer the presence of vast, faint loops and streamers dancing in a distant star's corona, effectively using starlight to paint a picture of structures they can never directly see. This comparative stellar astronomy is revolutionizing our understanding of universal stellar life cycles. Our Sun is a relatively calm, middle-aged star, but the universe is filled with stellar teenagers raging with hyperactivity and aging giants in their final years. By applying our solar ghost model, we can now better interpret the extreme activity of young, rapidly spinning stars, whose powerful magnetic fields likely generate colossal, complex ghost formations that dominate their coronae and drive intense stellar winds. Conversely, we can study the faint, fading coronae of elderly red giants, where the processes that create these structures might be slowing down, offering clues about the future of our own solar system. This allows us to categorize stars not just by their mass and color, but by the complexity and dynamics of their magnetic atmospheres, creating a whole new taxonomy of stellar behavior based on the presence and nature of their own ghostly apparitions. Perhaps the most profound implication lies in the search for habitable worlds. A star's magnetic activity, revealed by these coronal features, directly impacts the space environment around its orbiting planets. A star prone to frequent and powerful flares and eruptions, which might be preceded by the destabilization of its ghost-like structures, could bathe nearby planets in harmful radiation, stripping away atmospheres and making the emergence of life incredibly difficult. By using the Sun as a detailed template, astronomers can now look at the subtle spectroscopic signatures of other stars to gauge the likely stability of their coronae. They can search for stars that have a magnetic personality similar to our Sun's one that produces the gentle, persistent flow of a structured slow wind rather than constant, violent outbursts. In this way, the study of solar ghosts transcends pure astrophysics. It becomes a vital tool in the quest to find other worlds that might, just might, harbor the gentle conditions necessary for life to arise and flourish, linking the haunting beauty of our Sun's atmosphere to the grandest question of all: are we alone in the universe? While the dance of solar ghosts plays out 93 million miles away, its rhythm subtly influences the very technology that defines our modern existence here on Earth. This connection transforms their study from a purely academic pursuit into a critical endeavor for safeguarding the infrastructure we depend on every single day. The bridge between these ethereal structures and our daily lives is built on the concept of space weather, the constant flow of charged particles and magnetic fields from the Sun that washes over our planet. A calm, steady solar wind creates a peaceful space environment, but when the Sun erupts or its magnetic field shifts, it can trigger a solar storm with the potential to disrupt the delicate electronic backbone of our civilization. Solar ghosts, as subtle indicators of the Sun's underlying magnetic mood, provide us with invaluable early clues about these impending shifts. Consider our global network of satellites, the unsung heroes of modern life. They enable global positioning for navigation, relay television and radio signals, facilitate international financial transactions, and gather essential data for weather forecasting and climate science. These sophisticated machines operate in the harsh environment of space, directly exposed to the Sun's fury. An intense blast of solar radiation, often preceded by magnetic instability signified by the evolution of ghost-like structures, can overwhelm a satellite's shielding. This can cause temporary glitches, permanent damage to sensitive electronics, or even complete failure, severing critical communication and data links. By learning to interpret the formation and behavior of solar ghosts, space weather forecasters gain a longer lead time. A large, complex ghost forming in an Earth-facing coronal hole could signal the impending arrival of a high-speed solar wind stream days in advance, allowing satellite operators to safely place their multi-million-dollar assets into a protective safe mode, preserving their functionality and lifespan. The impact reaches far beyond orbit, directly down to the power grids that light our cities and power our homes. When a coronal mass ejection, a billion-ton cloud of magnetized plasma, is hurled toward Earth, it can distort our planet's protective magnetic field. These rapid magnetic fluctuations induce powerful electrical currents in the ground itself, a phenomenon known as geomagnetically induced currents. These unwanted currents can flow into extensive power lines and transformers, overloading them and causing widespread voltage instability. The most famous example is the Great Quebec Blackout of 1989, when a solar storm collapsed the entire Canadian power grid in seconds, leaving millions without electricity for 9 hours during a frigid winter night. Solar ghosts often form in the magnetic environments that precede such ejections. Their study helps improve our models of solar activity, giving utility companies crucial extra hours to manage grid load, temporarily bring backup systems online, and protect vital infrastructure from catastrophic damage that could take months to repair. Even our global communication systems are vulnerable. High-frequency radio signals used by aviation, maritime services, and emergency responders travel by bouncing off a layer of Earth's upper atmosphere called the ionosphere. Solar flares and energetic particle events, which can be foreshadowed by certain types of ghost activity, drastically heat and distort the ionosphere. This can cause radio blackouts, severing communication for pilots on polar routes, ships at sea, and disaster relief teams operating in remote areas. Furthermore, the precise signals from global navigation satellite systems, or GNSS, which we know as GPS, are slowed and bent as they pass through a disturbed ionosphere. This introduces errors that can degrade positioning accuracy from a few meters to hundreds of meters, crippling everything from agricultural automation and surveying to the navigation systems guiding commercial aircraft. Understanding the solar precursors to these events allows for more accurate warnings, enabling users to anticipate and plan for potential degradations in these essential services. Ultimately, the goal is to evolve from simply reacting to space weather to proactively predicting it with the same reliability we now expect from terrestrial weather forecasts. Each solar ghost we observe and analyze adds another piece to the immense puzzle of solar behavior. By incorporating this data into sophisticated computer models, scientists are working towards forecasts that can provide specific predictions days in advance, not just general alerts. This would empower a wide range of industries to take preventative action. Airlines could reroute flights away from polar regions during high-risk periods to avoid radiation exposure for passengers and crew and maintain communication links. Pipeline operators could monitor for corrosive currents induced in their networks. Astronauts on the International Space Station or future lunar missions could take shelter in better shielded modules. The gentle, whispering signals of these solar phantoms, once fully decoded, hold the promise of becoming a powerful early warning system, transforming our relationship with the sun from one of vulnerability to one of resilient coexistence. So as we've journeyed together from the sun's brilliant surface to the furthest reaches of its ghostly corona, we've uncovered a story far richer than mere apparitions. These solar ghosts are not phantoms of the imagination but profound scientific realities, transient coronal filaments that map the sun's invisible magnetic architecture, act as potential sources for the solar wind, and serve as crucial clues in unraveling the enduring mystery of the corona's intense heat. They remind us that even our most familiar star is a place of endless wonder, where delicate, dancing structures larger than our planet materialize from the interplay of superheated plasma and immense magnetic forces, visible only through the lens of cutting-edge technology and rare celestial alignments. Their study represents a beautiful convergence of ancient human curiosity and modern scientific ingenuity. For centuries, these features were little more than fleeting glimpses and unverified reports, dismissed by many as optical illusions. Today, they are at the forefront of solar physics, thanks to missions like the Solar Dynamics Observatory and the Parker Solar Probe, which allow us to not just see these structures but to sample their very essence and understand their role in shaping the space environment that envelops our planet. This progress underscores a powerful truth about our quest to understand the cosmos. Every mystery solved reveals new, deeper questions, and every answer invites us to look further. The existence of solar ghosts ultimately teaches us a profound lesson about the universe, that significance is not always measured by brightness or violence. The most powerful forces can often be the most subtle, and the keys to understanding the grandest puzzles can lie in the quietest, most delicate details. These ethereal formations challenge us to refine our instruments, sharpen our theories, and maintain a sense of humble wonder in the face of the sun's complex beauty. They are a testament to the fact that there is still so much left to discover, not in distant galaxies, but right here in our own celestial backyard. What are your thoughts on these solar apparitions? Does the idea of a dynamic, hidden layer to our sun spark your imagination? Share your questions and reflections in the comments below. I love hearing your perspectives on these cosmic wonders. If you enjoyed this journey into the heart of our star's mysteries, make sure to subscribe and hit the bell so you don't miss our next exploration into the unseen forces shaping our universe. Until then, keep looking up and wondering about the infinite secrets waiting just beyond.